As the president of the Norwegian Academy of Science and Letters, it's my pleasure and privilege to announce the winner of the Abel Prize for 2017. Styret i det norske Vitenskapsakademi har besluttet å tildele Abel-prisen for 2017 til Yves Meyer for hans nøkkelrolle i utviklingen av den matematiske teorien om wavelets. The board of the Norwegian Academy of Science and Letters has decided to award the Abel Prize for 2017 to Yves Meyer for his pivotal role in the development of the mathematical theory of wavelets.
My name is Jon Rognes. I'm a professor at the University of Oslo and the current chair of the Abel Prize Committee. Here is our citation. Fourier analysis provides a useful way of decomposing a signal or function into simply structured pieces like sine and cosine waves. These pieces have a concentrated frequency spectrum but are very spread out in space. Wavelet analysis provides a way of cutting up functions into pieces that are localized in both frequency and space. Yves Meyer was the visionary leader in the modern development of this theory at the intersection of mathematics, information technology, and computational science. The history of wavelets goes back over 100 years to an early construction by Alfred Haar. In the late 1970s, the seismologist Jean Morlet analyzed reflection data obtained for oil prospecting and empirically introduced a new class of functions called ondelettes, or wavelets, obtained by both dilating and translating a fixed function. In the autumn of 1984, Yves Meyer recognized that a recovery formula found by Morlet and Alex Grossman was an identity previously discovered by Alberto Calderon. At that time, Yves Meyer was already a leading figure in the Calderon-Sigmund theory of singular integral operators. And this was the beginning of Meyer's study of wavelets, which in less than 10 years would develop into a coherent and widely applicable theory. The first crucial contribution by Meyer was the construction of a smooth orthonormal wavelet basis. The existence of such a basis had been in doubt, and as in Morlet's construction, all of the functions in Meyer spaces arise by translating and dilating a single smooth mother wavelet, which can be specified quite explicitly. Its construction, though essentially elementary, appears rather miraculous. Stéphane Mallat and Yves Meyer then systematically developed multi-resolution analysis, a flexible and general framework for constructing wavelet bases, which places many of the earlier constructions on a more conceptual footing. Roughly speaking, multi-resolution analysis allows one to explicitly construct an orthonormal wavelet basis from any bi-infinite sequence of nested subspaces of L to R that satisfy a few additional invariance properties. This work paved the way for the construction by Ingrid Daubechy of orthonormal bases of compactly supported wavelets. In the following decades, wavelet analysis has been applied in a wide variety of arenas, as diverse as applied and computational harmonic analysis, data compression, noise reduction, medical imaging, archiving, digital cinema, deconvolution of the Hubble Space Telescope images, and the recent LIGO detection of gravitational waves created by the collision of two black holes. Yves Meyer has also made fundamental contributions to problems in number theory, harmonic analysis, and partial differential equations on topics such as quasicrystals, singular integral operators, and the Navier-Stokes equations. The crowning achievement of his pre-wavelets work is his proof with Ronald Koifman and Alan McIntosh of the L2 boundedness of the Cauchy integral operator on Lipschitz curves, thus resolving the major open question in Calderon's program. The methods developed by Mayer have had a long-lasting impact in both harmonic analysis and partial differential equations. Moreover, it was Mayer's expertise in the mathematics of the Calderon-Sigmund school that opened the way for the development of wavelet theory, providing a remarkably fruitful link between a problem set squarely in pure mathematics and a theory with wide applicability in the real world. Okay, that's our citation. So it's a great pleasure for me now to give the word to Professor Terence Tao of the UCLA, who has agreed to give a presentation of the work of this year's Abel laureate, Professor Yves Mayer. Please.
Okay. Thank you very much. It is a great honor to present the work of Yves Mayer. As a graduate student, my original field of study was harmonic analysis, and he was already one of the heroes of the field even then. So, as you just heard, Yves Mayer has made many contributions to both pure and applied mathematics. In fact, many times he would first work on a subject motivated purely by theoretical considerations, and only later would it be realized that it actually had a great impact in applications also. So, for example, in his early work on quasicrystals is a great example of this. Yves Mayer was studying a question of purely theoretical interest. He was studying the distribution properties of certain special numbers called Poisson numbers, like the golden ratio, that have many interesting number theoretic properties. And he found that these numbers were related to a certain type of set, which we now call a Mayer set. And these are examples of sets that are not quite periodic in that they don't repeat themselves regularly, but they are what's called quasi-periodic. They repeat themselves, but not in a regular fashion. For example, on this line here, you see these green dots. This is an example of a one-dimensional Mayer set, these green dots. It's not quite periodic, but it has patterns that repeat themselves. So, for example, you see here there's a short interval between these green dots and then a long interval. And then it repeats. Again, you have a short interval and then a long interval. But then it doesn't repeat. There's a long interval, and then there's a short interval and a long interval. So there are repetitions of patterns, but the repetitions are irregular. So it is not periodic, but it's what's called quasi-periodic. It does share many features in common with periodic sets. They have a very similar Fourier spectrum, for instance. On the left here, we have a two-dimensional example of a quasi-periodic set. So you can see several patterns in the set repeat themselves. For example, there's a little circle here, which again repeats itself over here, and then it repeats itself over here, sort of, but not quite. The repetition is imperfect, and the gaps are not completely regularly spaced. So it is not perfectly periodic, but it does resemble a periodic set in many ways. These are these quasi-periodic sets. And Mayer developed a theory for describing these sets and how to build them. One of the most important realizations he had was that you can describe these quasi-periodic sets in terms of periodic sets of higher dimension. So, for example, on the right-hand side, this one-dimensional quasi-periodic set of green dots, you can actually construct using this higher dimensional periodic set of black dots. So these black dots are arranged in this lattice. This is a completely periodic set. You can look at the black dots inside this strip. Between these dotted lines, there's a certain number of black dots. And if you project those black dots onto this line, you create this Mayer set, this quasi-periodic set here. So you can create this quasi-periodic set from a higher dimensional periodic set. And similarly, this complicated quasi-periodic object actually comes from a higher dimensional periodic object. So this was his theoretical work. 10 years after his work, chemists actually discovered quasicrystals in real life. They actually discovered arrangements of matter that were not periodic, but exhibited quasi-periodic structure exactly as described by Mayer. In fact, Dan Shechtman won the Nobel Prize in Chemistry for his discovery of quasicrystals. Another area that Mayer has worked in is the study of partial differential equations, particularly fluid equations like the Navier-Stokes equations. These are equations that govern fluids like water or air. They're used in weather prediction. They're used to model aerodynamics of planes and so forth. But they're very complicated equations, and we still don't fully understand them, or even how to solve them for long periods of time. And one of the main reasons for this is the phenomenon of turbulence, that when you solve these equations, you may have initial conditions that are very smooth, that have no fine-scale structure, but as you evolve the equation, the fluid mixes with itself, eddies appear, and energy gets transferred to finer and finer scales, and you get very complicated behavior, which becomes very hard to numerically simulate. The theory of these equations is still not fully resolved. For example, development of singularities. But Mayer has worked on this, and using his theory of wavelets, for example, he has clarified it, to some extent how energy can be transferred from low frequencies to high frequencies, and so forth. But that's not the focus of my presentation today. I will be talking about the main thrust of his the most famous work, and the one that he was most recognized for in the Abel Prize, which is his being one of the founders of the theory of wavelets. So wavelets are these special functions which have some oscillation and some spatial localization and some additional properties too, which make them very useful for signal processing. So signal processing, this is the study of, it is the science of digital data. And nowadays, digital data is everywhere. Anytime you have a computer or a phone or a tablet or the internet, you're always dealing with digital data. And there's many, many types of digital data that we have to deal with. But from a mathematical point of view, you can treat many, many classes of data in the same mathematical framework. So for example, sound is a good example of digital data. A sound wave, here's a sound wave. Mathematically, you can think of it as one-dimensional data. The dimension is time. And for every point in time, there is some amplitude, and that's a sound wave. And so mathematically, it's just a one-dimensional function. We also have two-dimensional data. Here's an image of a famous museum in Oslo. And it is a two-dimensional piece of data. Okay, so the two dimensions are x and y, width and height. And for every point in x and y, you have some color or some intensity. So you have some function of two variables, two-dimensional data. And then you have three-dimensional data, like videos. So a video looks flat, looks two-dimensional, but it's actually, from a mathematical point of view, it is actually three-dimensional data because there's also time. So for every x and y, and for every time, there is some color or some intensity, and that function of three variables describes a video. And in signal processing, we also study 4 and 5 and 6 height. You know, we study data of any dimension. But but all this type of data, you can treat all of them using the theory of wavelets. So when you analyze data digitally, you have to represent the data by decomposing it into manageable pieces, into simple components. So one of the most direct and obvious ways to represent data is to take a spatial representation, or if it's a time series, a time representation. And that just breaks up your signal into individual data points localized in a single point in space or a single point in time. So for example, if you have an image, you can represent the image as a bitmap. This is the basic example of a spatial representation. You decompose every point in this image into, you call them pixels, and every pixel you have a color and intensity, and you just store the colors one by one as an array, and this is a bitmap representation of this image. So this is it's good for some things. It has no loss, and it is very good for discerning the very fine scale structure of your image. But it's very inefficient spatially in terms of how much storage space you need to store the image. For example, an image like this, it might take 1 million pixels to represent this image. And also, it's very hard to see large-scale structure. Right? If your computer just sees an array of pixels, it is not immediately obvious how to program the computer to recognize that this is a deer, for instance. At the other extreme, another type of representation is the Fourier transform, which is now about 200 years old. So This is the opposite, in many ways, of spatial representation. You take a signal, like maybe the sound wave or some other sort of wave here, and the mathematics of Fourier analysis lets you decompose this wave into plane waves, sinusoidal waves, the sine and cosine waves from trigonometry. Sometimes you can represent a wave using just a finite number of these plane waves, Fourier modes. Sometimes you need an infinite number. But thanks to Fourier and his descendants, we know that we can always do this. Pretty much any signal can be written as a superposition of sinusoids. And you can use that to store and analyze your data. This is very useful for many applications. For example, if you want to understand large-scale oscillations, like, for example, seasonal variations in some time series, then the Fourier transform is very good for that. But it is very hard to see fine-scale structure. So, very fine-scale features, like corners and edges of an image are difficult to discern using the Fourier representation. And in terms of storage, it is just as inefficient as the spatial representation. So the wavelet transform, the wavelet representation, combines the best of both worlds of the spatial representation and the Fourier representation. So it is a representation which, like the spatial representation, it is very localized. You can see fine-scale features. But like the Fourier representation, it also has the ability to detect large-scale structure. So here's a comparison of the two, of the Fourier representation and the wavelet representation for a single image. This is a single simple signal here, this spiky wave here. So the Fourier transform would decompose this signal into an infinite number of these sinusoids. Whereas in contrast, the wavelet transform would decompose the same signal into an infinite number of wavelets, which oscillate a little bit like the sine wave, but whereas these sine waves oscillate forever, they have no spatial localization, the wavelets are cut off in a certain special way to become almost zero or exactly zero after a certain point. So these are both representations, but there are certain advantages to the wavelet representation. So when you decompose this particular signal, you actually need an infinite number of sinusoids. If you keep just the most important ones, the 7 biggest Fourier modes here, if you reconstruct the signal just using these 7 modes, you get a rather poor reconstruction. The sharp corners have been rounded off to something fuzzier here, and you get all these oscillatory artifacts which don't represent the true signal. But if you instead use a wavelet basis to approximate the original signal, you get a much better reconstruction. The edge features are much more faithfully reconstructed, and there are fewer artifacts of oscillation coming from the representation, with even just 7 of these wavelets. So a key feature of the wavelet transform, which underlies so many of its applications, is something called sparse representation. So I told you that if you represent, say, an image, either as a spatial representation or as a Fourier representation, you need a lot of storage space to store all the data. For example, this is an image of the Golden Gate Bridge in San Francisco. You notice that most of the pixels here are white or brown. You have to store all of these pixels if you want to store the bitmap. If you only store a fraction of the maybe 100,000 or so of the pixels here, you'll have big holes in your image. But if you take a wavelet transform, so there's a certain special type of wavelet transform called the Haar wavelet transform, which is what is being used here. You can break up this image into wavelets. Over here, these are the finest scale wavelets, the narrowest wavelets. These describe the finest scale structure of this image. For example, these cables here are fairly well represented by this the fine scale. And then there's some medium scale features like the main structure of the bridge. And then over here are the coarsest components of the image, like the background sky and so forth. But one thing you notice when you apply this transform is that most of the coefficients here, most of the image is black. So most of the coefficients here are either 0 or close to 0, which means that you could actually discard 90% of the coefficients here, just keep the significant ones, and you still get a very good representation of your image. So you have this very sparse way to describe almost all of your image. And so the wavelets have this sparse representation property when applied to many classes of real-world data. So this type of sparse representation property has many, many applications. Many modern routines in signal processing rely on the ability to find a sparse representation of your data. And in many cases, the sparse representation of choice is the wavelet representation. So for example, image compression was the first example. If you want to compress an image to something smaller so that you can take more pictures on your phone, or you can send images over the internet faster, you need to compress your image. So you don't use bitmaps, you use maybe GIFs or JPEG format. One of the major formats for image compression is JPEG 2000. And that particular format actually is exactly using the wavelet transformations developed by Meyer and his collaborators. There's also applications to denoising. If you have, say, a sound signal or video signal which has a lot of artifacts, a lot of interference, noise, you can use wavelets to remove the noise and keep the portion of the data that you actually want to keep. If you want to detect features like edges, you have an image of a face, you want to find out the boundaries of the face, where the eyes and ears and mouth are, you can use wavelets to help with that. You can solve differential equations, like the fluid equations, numerically, using the wavelet basis. It can be a very convenient basis for many of these applications. Actually, nowadays we used descendants of wavelets, other bases which were adapted from the original wavelet decomposition. There's a lot of CGI which involves wavelets, especially when you model any kind of object with both fine scale and coarse scale structure. So curves and surfaces with some sort of ripples in them. And anything like that is good for, suitable for wavelet representation. A more modern application in the last 10 years is compressed sensing. This is a way to, a new paradigm for taking measurements of data, in some sense trying to measure the wavelet coefficients of an image or some other source more or less directly, rather than taking an entire image with high resolution and then extracting the wavelet coefficients afterwards. So this is something actually I worked in a few years back. And it's used, for instance, to speed up magnetic resonance imaging. An image that might have taken 2 minutes to scan a human body, it can now take 10 seconds using these compressed sensing methods. And they're all based on sparse representations, and many of these algorithms use wavelets. So wavelets come in many forms. There are many types of wavelets, and they're suitable for different applications. One of the main early contributions of Meyer was the development of a general theoretical framework, in particular his multi-resolution analysis framework with Meyer, which allows one to design wavelets sort of a la carte. That if you want a wavelet with a certain property, you can find one. So if you want a nice simple wavelet, maybe you can take this Haar wavelet here. If you want a smooth wavelet, you can maybe take Meyer's original wavelets. If you want a compactly supported wavelet, you can take Ingrid Daubischi's wavelet, and so forth. There are many wavelets used now in various applications, and which one to use depends on what application you want to do. But they can all be generated by Meyer's sort of unified framework. So that's just a small taste of what he has contributed to mathematics. So I think that is the end of my presentation. Thank you. So at this stage, the tradition is that we now call the Abel laureate to congratulate him and ask him a few questions. Unfortunately, he was not available to take the call live. However, we did record a conversation with him just a few hours ago, so I think that will be played next, right now. Okay.
So go ahead.
All right. So Okay, so first of all, congratulations on your Abel Prize. It's very well deserved. So how do you feel, actually?
I am, yes, I feel at the same time happy, surprised, and slightly guilty.
I can understand that.
You can understand.
Yeah. No, yeah. So, can you describe how where you were and how you were notified of the prize?
Yeah, I was in my home, and I was called at 9:15 from I think the Academy of Science and Letters of Oslo, and I received the announcement this morning.
Mm-hmm. Okay. What was your immediate reaction?
It was such a surprise that I was, it was a shock. My reaction was being slightly shocked by the news.
Yeah, maybe it will probably take a while to recover. So, about mathematics. So,
Yes.
you're being recognized for your work in wavelets. So,
Yes.
you saw the connection between the empirical wavelet transforms that were being used in science and the reproducing formulas used in harmonic analysis by Calderon.
Yes.
So,
yes.
how did you find this connection? What made you?
The story is very interesting. I was working at École Polytechnique.
Mm-hmm.
Nearby is a group, a department of mathematical physics. And the head of the department, Jean Lascaux, he was a very open-minded guy, and he loved discussing with me. He was reading almost everything, and he was always making Xerox copies. And we had only one Xerox copy machine, in such a way that for making a Xerox copy, I had to wait he finished. And I loved waiting and discussing with him. And one day, he said to me, "Yves, I received just this paper, this preprint from Alex Grossman. I am sure that should interest you." So he gave me the preprint, and it was the first work on wavelets. So Alex Grossman is a physicist.
Mm-hmm.
He has a joint work with Eli Stein.
Oh, yes, my advisor.
On quantum mechanics. So there is a paper by Eli Stein and Alex Grossman. Mm-hmm. And I immediately recognize Calderon reproducing formula, but the great news is that this was already applied by Grossman and Morley, who was an engineer at Elf Aquitaine, an oil company, and Morley was using this tool for oil prospection. So the story began before I entered the group. It is very interesting. What they used is continuous wavelets, so the computation load was heavy, and my only merit has been to find orthonormal basis, which led to the rapid computational. And on the other hand, I just formed a piece of the whole building because Stephen Mallat understood, who is almost a student of mine, but not in the strict sense, because he worked in a very independent way, found the connection with quadrature mirror filter, which was a tool which was already used by electrical engineers. So the landscape was open to application through this connection. So the connection through orthonormal wavelet basis and by Stephen Mallat quadratic mirror filters.
Okay. It's quite an involved story.
It is very surprising because the beginning is just like a fairy tale.
Yeah, no, it was quite serendipitous. So this Abel Prize is recognizing both contributions to pure and applied mathematics, which is
Yes.
unusual for the Abel Prize, actually.
Yes.
So in your opinion, how do the two fields of mathematics relate to each other? Do you view them as a unified subject or as separate?
Yeah, to me, the way I am working is more or less following the philosophy of a movement which sprang in the States in the 50s, just after the war, and which was called the Center for the Unity of Science. And this was founded by von Neumann and scientists coming from Vienna, who belong to the Vienna Circle. So this, in that time, in the early 50s, people recognized that ideas coming from signal processing, from telecommunication, from mathematics, and even linguistics could be unified with in a very deep way, leading to a new science. And the objective was also to extend the teaching of science, that this unified viewpoint would make the teaching easier. There was a beautiful contribution in Daedalus, which is a publication of the Academy of Arts and Science about this movement for the unity of science. And for me, it opened my eyes, and I felt it was exactly what I was doing all the time. This unified view. And in the case of wavelets, for example, the fact that I worked with a physicist in quantum mechanics like Alex Grossman, with an engineer, and suddenly with people in electrical engineering, for example, was a kind of happiness. I was this large land scale. In the case of wavelets, there is even a more beautiful story. It is a discovery by David Huber and Thorsten Wiesel of neurons which are specialized in detecting edges in images, in the image received by the retina. And the way these neurons detect edges is exactly an application of the wavelet transformation. So that has been made explicit by Huber and David Marr in his beautiful book, in such a way that the landscape was even broader, It included the understanding of the brain. Wow. So, and then I reached a kind of happiness I've never experimented before.
Ah, it's great to see science being so unified in your worldview.
Yes.
So, what are you thinking about nowadays? What
nowadays about wavelets, what I feel very happy because it sprang a new piece of mathematics called compressed sensing, which has been developed by Emmanuel Candes. Mm-hmm. And I am also extremely happy because Emmanuel Candes was my student in the qualifying exam. So he took my qualifying exam in Paris, but then he wanted, for some personal reason, to study abroad. So I decided that I could propose him to study with David Donoho. And then David Donoho, after Emmanuel Candace completed his PhD and obtained his first spectacular result during a conference that he was doing, made the following statement, that sending Candace to the States was the best service I made to science, which is a very funny statement, and I love that. So, Emmanuel Candace wrote the post-wavelet novel, and his theory of compressed sensing is something extremely beautiful and application to image processing. And then I cannot prevent me from mentioning your joint work with Emmanuel Candace.
Oh, thank you. Yeah, it was mostly Candace's work, actually. Yeah. No, that was a great collaboration. Well, it was great talking to you, Yves, and congratulations again. And
thank you.
Hope to see you in May in Oslo.
Yes, thank you very much. Thank you for calling.
Okay.
Have a good day.
I would like to thank the audience for coming here today. The announcement of this year's Abel Prize laureate will be followed up at the House of Literature in Oslo tonight. At 6 p.m., the public is invited into the realm of mathematics. The work of the Abel laureate Yves Meyer will be presented by Terence Tao. TV host and science journalist Eldrid Borgan and Magnus Deli Vigeland, mathematician and professional circus artist, will guide us through the evening. I also have the pleasure of welcoming you to the Abel Prize Awards ceremony at the University Aula in Oslo on Tuesday, 23rd of May at 2 p.m. Yves Meyer will receive the Abel Prize from His Majesty King Harald V. The ceremony will be followed by a reception at the Norske Teater, where TV host and journalist Nadia Hasnaoui will interview the laureate. You are most welcome to join us in celebrating Yves Meyer.